somewhat as a practice exam question, but also kind of a teaching question. It's far from trivial. Let's see. Any answers for the first part here? Anybody willing to volunteer? 31. Any other answers? 6.9. Nobody else? You got 6.9 as well, so got two 6.9s. Okay. All right. So let's try to tackle this. So I said this is a challenging problem. And let's draw a picture. So I didn't provide a picture. So sometimes that can be the challenge, just the visualization of the problem. So we've got a 35-degree incline, and we're launching a block up the incline with initial speed of 10 meters per second. So as the block moves up the incline, I can draw a free body diagram for the object. So it has a weight force going down. This part is not really important. I really want the component that is parallel to the incline. So this piece here, which I hope most of you know at this point. If I give you the angle from respect to the horizontal, this is mg sine of theta. And since it's moving up the incline, well, there'll also be a normal force here as well. Again, not important for the question because, again, it doesn't affect the motion parallel to the incline. It also has a friction force going down the incline. So this is going back to, again, Newton's. This is basically, from my point of view, exactly like the cart problem from question 1, the sled problem in whatever that was 3 or something like that. And I just basically add in an incline and I add in friction. So, but from the way I'm going to solve it, as you'll know, is exactly the same as those previous problems. I'm just going to make sure I get out my own way here. Okay, first going to solve for the net force. So the net force on the, let's say, block is going to be negative mg sine theta. So that, and I'm going to make down the ramp positive. Do I want to do that? It doesn't really matter. I'll keep it negative. Minus the friction force, Fk. So that's really equal to minus mg sine of theta minus mu k mg cosine of theta. So where the mg, this piece here is the mg cos theta. So that's the normal. So that's the difficulty in doing ramp problems, is that the normal is not equal to mg because it's on a ramp. So it doesn't have the full component of the weight force straight down. So you decompose the weight vector into a vector down the ramp, vector parallel to the ramp. So again, another why I emphasize vectors in the first couple of slides. And they're both working against the block on the way up the ramp. So if you want, I'll give you a second if you want to do your calculations here, plug in you could take the mg part out here, negative mg sine of theta minus mu k cos of theta. Go ahead and plug that into your calculators if you'd like. And you should end up with, I didn't do that calculation on my Excel. Should be negative 14.5 newtons. So about 11.2 for the weight, and then another 3 for the friction. So now we know we can figure out the acceleration of the block by just dividing the 14.5 newtons divided by the mass of the block, 2 kgs. So that should give us the negative 7.2 meters per second squared. So it's just, in a sense, think about what we did with the cart, think about what we did with the sled. It's just more challenging because I've added in a friction and I've added in an incline. But that's how you step up a problem. I know you're probably sick to death of like inclined plane problems, but it's sort of it's a way for us to sort of like, I'm tired of doing horizontal table problems. Let's throw in a ramp and see what happens. They're more challenging. You got in some trig. Questions so far? So once you decompose it, so the weight force is straight down. This angle in here is theta. If the horizontal line, if this angle here is theta, so the hypotenuse of this right angle triangle is mg. So the adjacent side is mg cos. The opposite side is mg sine. This is the theta up here at the top. Yeah. Yep. Yep. On the way up. The velocity can be up the ramp, but the A down, slowing down. It has to actually, like you know yourself, it has to. If the V is positive, then the A has to be negative going up the ramp. Otherwise, it would be speeding up the ramp, which would, unless it has its own motor, it's not possible. Okay, so if we have the acceleration when it comes to rest, so that sort of code here that the final velocity is 0. So I want to know how far along the incline the block travels without any time. I've got the V's, I've got the initial velocity, I've got the final velocity, I've got the A, I'm looking for delta x, so I'm in my VF squared formula again. So VF squared equals VI squared plus 2A delta x. So the delta x will be equal to minus VI squared over 2A. So that'll be minus 100. So once you square the 10, and this minus is outside of the square piece. It's not. You first square the velocity, and then you put this minus in here. That's why I don't worry too much about the signs. Divided by 2 times this acceleration. And congrats to those who got the 6.9. Not an easy problem.
So is the force of friction not acting in the system?
The kinetic friction forces. Only kinetic, because it's moving. So the static stuff is in there to throw you off. This life throws you off. You think you're going to face a patient that's going to tell you like, here's my diagnosis. Just give me the right pills. Your job is to figure out problems, and you'll have distractors. The patient will have some sort of like random sort of thing that might not be linked to the person's problem. This is life. Life that you're training for, I'm guessing. A far majority of you life science majors, right? Any questions? 6.9. Well, it gets the 0.5 is not technically in there, just for it's not in there completely to be a distractor. So when the block gets to the top, how do I know it comes back down? What if the gravity's that? What if it gets stuck up there? Isn't that possible? Have you ever pushed something up a ramp and it sticks? Yeah. Right? So what is the max static friction force? Fs max is mu s mg cosine of theta. That's 0.5 times 2 times 9.8 times the cos of 35. You can do that in your calculator if you want. And it should bring you out to an 8.0 newtons. I want to make sure I'm still recording this. Yep. These files are almost like a gigabyte. And it's an entire canvas size. Where am I going with this? So that's the maximum for static force. When it gets to the top, what is the weight force component? So the weight along the ramp is mg sine of theta, and you'll find that this is equal to 11. So even when it gets to the very top, when it comes to instantaneous rest, the weight force is dragging it back down the incline. It's still going to be bigger than the max static. There's no way for it to get stuck at the top. So that's why the 0.5 is in there. But since I'm asking you how fast it's moving when it gets to the bottom, you can probably assume it doesn't get stuck up there. Any answers? I guess so. Again, if you didn't answer the first one right, it's impossible to get the second one because we need to know the distance now traveled on the way down the ramp is 6.9 meters. Maybe go with that. Maybe to give you an extra challenge. The distance traveled is 6.9 meters. See if you can now find. Give you maybe another couple minutes. See if you can find the speed at the end. I'll pause the video and maybe I'll do this as a two-parter.